In the last lecture, I have introduced the concept of random variables. So, the motivation for defining random variables is that most of the random experiments and their outcomes, if we look at the complete description of that, it may be quite complex. Whereas, we may not be interested in the full description of the phenomena. We may be interested in a particular numerical phenomena connected with the random experiment. Therefore, we define random variable as a real valued function defined on the sample space. Now, once we have a probability space omega b p, and if we are defining a random variable x on omega, then naturally the probabilities which are associated with the points in the sample space get translated to the values taken by the random variable. This correspondence between the probability allotment with the values of the random variable is called probability distribution. In the previous lecture, I introduced the concept of a cumulative distribution function. We showed that it is having a one-to-one correspondence with the probability distribution of a random variable, and at the same time it gives almost all the information about the random variable. Now, random variables are of different types. We have the cases where the random variable can take a finite number of values or countably infinite number of values or uncountably infinite values, which we say that lying in an interval. So, the first one we called a discrete random variable. The allotment of the probabilities for a discrete random variable we call a probability mass function. So, let me give one more example of a probability mass function. Consider the following: a package of 4 bulbs contains 1 defective. The bulbs are tested one by one without replacement until the defective is detected. Find the probability distribution of the number of testings. So, let us look at x is the random variable which denotes the number of testings. Once we outline a random variable, first thing is we should look at the set of values that the random variable can take. Here, if we test it once, that itself may be a defective, or if that is not so, second one may be defective, or if that is not so, the third one may be defective, or if that is not so, the fourth one may be defective. However, we should look at here that if the third one is found to be not defective, since there are only 4 bulbs in the package, so the fourth one will be automatically treated as the defective. So, we in reality do not need the 4 testings, we need only 1, 2 or 3 testings. So, what is the probability of x is equal to 1? Now, there are 4 bulbs out of which 1 is defective. So, the probability that the first testing gives you a defective will be 1 by 4. What is the probability that the second one is defective? So, that means the first one must not be defective. Now, there are only 3 bulbs left, out of that 1 is defective. So, the probability of that is 3 by 4 into 1 by 3, that is equal to 1 by 4. If we look at Px3, that is probability of x equal to 3. Now, by the direct logic, it should be simply 1 minus the probability of x equal to 1 and probability x equal to 2. So, it should be half. Let us see how it can be evaluated directly also. So, the first one is not defective, second one is not defective, and the last one is defective, but this is equal to 1 by 4. We should also take into account the possibilities that the third one is non-defective, because either it is defective or not defective. In both the cases the outcome is known that the fourth one is will be defective or not. So, it is actually equal to half. So, this is the probability distribution of the random variable x, which is the number of testings required. Next, let us define the probability distribution of a continuous random variable. So, what is a continuous random variable? So, we say that a random variable x is continuous if its CDF is an absolutely continuous function. A random variable x is said to be continuous if its cumulative distribution function f is absolutely continuous function. That is, there exists a non-negative function small f x such that capital F x is equal to minus infinity to x f t dt for almost all x. Basically, it should be for all x belonging to R. The function f x is called the probability density function of x, or PDF. If f is absolutely continuous, and f is continuous at x, then d by dx of f x is equal to small f x. The PDF or the probability density function satisfies one, that it is a non-negative function. Secondly, the integral over the full region is equal to 1, and if we integrate the density over an interval a to b, it is denoting the probability of a less than or equal to x less than or equal to b, that is basically f x b minus f x a. Now, the continuous random variable is quite different from the discrete random variable. So, the first thing that we noticed here is that in the discrete random variable we had a probability mass function. So, p x I, it denoted the probability that the random variable x takes values x I. Here at the point x we have a density function f x. Now, this is, one should not get misled and say that this is probability that capital X equal to small x. In fact, in the discrete case, the mass function defines the probability of that point. In the continuous case, it does not define. In fact, probability of every point is 0. So, that is a important observation. To prove that, let us see firstly that for any random variable x, probability that x is equal to a is equal to limit probability t less than x less than or equal to a, t tends to a where t is less than a. So, if we denote, let us prove this statement. Let us consider say t1 less than t2 and so on, tn goes to a, and write an to be the set that tn is less than x less than or equal to a. Then this is a non increasing and limit of an will be equal to intersection of an, which is basically equal to x is equal to a. So, limit of probability of an is equal to probability of limit an. This statement is equivalent to limit t tending to a, t less than a, probability t less than x less than or equal to a is equal to probability x is equal to a. Now, this is actually equal to limit f a minus f t, where t tends to a, t is less than a, which is exactly equal to f a minus the left hand limit at a. So, if f is absolutely continuous function, then probability x equal to a will be equal to f a minus f a minus is equal to 0. So, for a continuous random variable, probability that x is equal to some value c is 0 for all c. Let us consider some examples here. Let x be a random variable with CDF fx is equal to 0 for x less than 0, it is equal to x for 0 less than or equal to x less than or equal to 1, it is 1 for x greater than 1. Quite obviously, this is a absolutely continuous function, and in fact, you can plot it. For x less than 0 it is 0, for 0 to 1 it is x, and thereafter it is 1. So, the density function is given by 1 for 0 less than or equal to x less than or equal to 1, and it is 0 for x lying outside the interval 0 to 1. Let us consider some more examples. Suppose fx is given by 10 by x square for x greater than 10 and 0 for x less than or equal to 10. I want to find out what is the probability 15 is less than x less than 20. Then it will be equal to integral from 15 to 20 10 by x square dx, that is equal to minus 10 1 by x from 15 to 20, that is equal to 10 1 by 15 minus 1 by 20. So, 2 by 3 minus half, that is equal to 1 by 6. If we want to find out the CDF here, then it is minus infinity to x ft dt. Now, here the positive value of the density starts from the point 10, therefore, it will be 0 for x less than 10, and thereafter it will become 10 by integral of 10 by t square. So, that will give me from 10 to x for x greater than or equal to 10. So, it is equal to 10 by t from x to 10, that is equal to 1 minus 10 by x. This is for x greater than or equal to 10. So, if you want, you can plot this function up to x equal to 10, it is 0, and at x equal to after that it becomes 1 minus 10 by x. So, the function is increasing because 10 by x is decreasing function. As x tends to infinity, this goes to 0, that means it goes to 1. In fact, if you look at the derivative of this, so it becomes like this, basically a concave function. This is suppose 1 here. Let me take one more application of this. Suppose x is a continuous random variable with the density function, say x by 2 for 0 less than or equal to x less than or equal to 1, it is half for 1 less than x less than or equal to 2, it is 3 minus x by 2 for 2 less than x less than or equal to 3. It is 0 at all other points. First thing is, we should notice whether it is a proper probability distribution. Then the integral of f(x) dx over the full range must be equal to 1. Obviously, it is non-negative function. So, this will be equal to integral 0 to 1 x by 2 dx plus integral 1 to 2 1 by 2 dx plus integral 2 by 2 to 3 3 minus x by 2 dx. So, if you integrate each of these terms, it becomes, in fact, half can be kept outside, then you will get half plus 1 plus here 3 minus x square by 2. So, it becomes 9 minus 4, that is 5 by 2. So, clearly this is equal to 1. If we want to write down the cumulative distribution function of this, then minus infinity to x ft dt. So, for x less than 0, we are integrating only 0. So, this will be equal to 0. In the other regions, for 0 to 1, we have to integrate the term t by 2 dt from 0 to x. If we look at x lying between, so this is for x less than 0, for x between 0 to 1, we have this term, for x between 1 and 2, we have 0 to 1 x by 2 or t by 2 dt plus 1 to 2 half dt, that is 1 to x. It will be 0 to 1 t by 2 dt plus 1 to 2 half dt plus 3 minus t by 2 dt from 2 to x. and it is equal to 1 for x greater than or equal to 3. So, if we simplify these terms, we will get here, let us look at this one, it is equal to x square by 4. Here up to 1 it has been integrated, therefore, this will be 1 by 4 plus x minus 1 by 2. Once again here if we have integrated up to 2, then this value would have become 3 by 4 plus the value of this term, that is 3 minus t whole square by 4 from x to 2, which will be some value. It is 1 for x greater than or equal to 3, 0 for x less than 0. So, here you can see this function will be having different values. X square means it is a convex function up to 1, then thereafter it is a line, and thereafter again it is a parabola kind of function, which is actually in the reverse. So, it will go up to 1. However, in each case if you differentiate it, you will get the density function. If you want to find out probability of a certain set, suppose I say what is the probability that x lie between half to 5 by 2, then it will be integral of x by 2 from half to 1 plus integral of half from 1 to 2 plus integral of 3 minus x by 2 from 2 to 5 by 2, which can be evaluated after certain calculations. There is also a possibility that random variable may be partly discrete or partly continuous. These are known as mixed random variables. Let me consider some example. Consider for example a person traveling to his office every day by car. On the way to the office there is a traffic crossing. It may happen that some of the days the traffic crossing has a green signal when he approaches the traffic light and he crosses without waiting. On the other days there is a red light and he has to wait for a certain amount of period. In other words, he may have, if I say x denotes the waiting time at traffic signal, it may happen that probability that x equal to 0 is say 1 by 4. That means 25% of the time he is able to go without waiting. On the other hand, if he has to wait, then it is a continuous distribution. He may have to wait for 0 to 1 minute. If we see the total allotment of the probabilities, in this case the probability of 0 less than x less than or equal to 1 is actually equal to 3 by 4. So, probability x equal to 0 and probability of x lying between 0 to 1 is 3 by 4. So, if you add up these two, it is actually becoming equal to 1. But here the distribution is not for totally discrete or totally continuous random variable. We can also look at the CDF of this particular random variable. At before x equal to 0 it is 0, at x equal to 0 it is becoming 1 by 4, and thereafter it is becoming 1 by 4 plus integral 3 by 4 dx from 0 to x. And of course, it is equal to 1 for x greater than 1. So, if we expand it, it is becoming 0, x less than 0, 1 by 4 for x less equal to 0, and here it is becoming 3, 1 by 4 plus 3 by 4 x for 0 less than x less than or equal to 1. It is 1 for x greater than or equal to 1. You notice here that the function is not continuous at x equal to 0, and therefore, in fact there is a jump point. The right hand limit and the value at x equal to 0 is 1 by 4, whereas the left hand limit at 0 is 0. So, there is a jump of size 1 by 4 at 0. So, that shows that discrete nature of the random variable at x equal to 0, whereas after 0 to 1 it is a continuous random variable. So, this is an example of a mixed random variable. If we plot this particular distribution CDF, then up to 0 it is 0, at 0 it is becoming 1 by 4, then from 1 by 4 to 1, it is increasing and it is 1. So, in this case it is a continuous random variable, there is a jump here of size 1 by 4. Next, we consider the concept of moments. Or mathematical expectation. Let x be a discrete random variable with probability mass function, say Px xi for xi belonging to some set x. So, we define the expected value of x as E of x. This is defined as sigma xi into Px xi, where xi belongs to x, provided the series is absolutely convergent. Let us consider some examples. Let us take the example of defective computers purchase. That means a store had certain number of computers and a person purchased 2 computers. So, in that example we had probability of x equal to 0 was 10 by 21 by 45, and that was same as probability of x equal to 1, and probability x equal to 2 was 3 by 45. Let us look at expectation x. So, that will be equal to 0 into 21 by 45 plus 1 into 21 by 45 plus 2 into 3 by 45. So, that is equal to 27 by 45 or 3 by 5. That means, on the average his purchase may include less than one defective computer. Let us look at the next problem of, that is Px1 was 1 by 4, Px2 was 1 by 4 and Px3 was half. That is the number of trials needed for getting the defective bulb. Here expectation of x is equal to 1 into 1 by 4 plus 2 into 1 by 4 plus 3 into 1 by 2, which is equal to 9 by 4, which is actually greater than 2. That means on the average you will need more than 2 testings for getting the defective bulb. You notice here that we have not checked the condition of absolute convergence here, because that number of terms is only finite. The condition is needed actually in order that the expectation is well defined. Consider say probability that x is equal to minus 1 to the power say j plus 1, 3 to the power j by j factorial, say j is equal to 2 by 3 to the power j, j is equal to 1, 2 and so on. Let us look at sigma modulus of xj, probability x is equal to xj, j is equal to 1 to infinity. Then this is equal to sigma 3 to the power j by j factorial by j 2 divided by 3 to the power j. Now this is divergent. So expectation x does not exist. Although one may write here sigma xj probability x equal to xj, and here you will get minus 1 to the power j plus 1 2 by j, which is having value log 2, but it is not absolutely convergent. Therefore, expectation x does not exist here. So this expectation x is also called average value, it is also called mean of x or arithmetic mean of x, etc. So several names are there. It is also called the first moment about the origin. If x is a continuous random variable with PDF fx, then expectation x is defined as integral minus infinity to infinity x fx dx, provided the integral is absolutely Let us look at some of the examples. The first example here we had in the continuous case, fx was 0 for it was 1 for 0 less than or equal to x less than or equal to 1, and it is 0 otherwise. So expectation x will become equal to integral x into fx, that is equal to 1 in this interval, and therefore you will have basically only this term which is equal to half, which looks reasonable also, because if you plot this distribution from the 0 to 1 interval, it is actually constant value, and therefore the mean value must be middle value, that is half. Let us look at the next example. Fx is equal to 10 by x square for x greater than 10. I am skipping the other part here, 0. So integral x 10 by x square dx for 10 to infinity. So that is equal to 10, and integral of 1 by x is log x for 10 to infinity. This is divergent. So here expectation x does not exist. Let us consider another example. fx is equal to x by 2 for 0 to 1, it is half for 1 to 2, and 3 minus x by 2 for 2 to 3. For this example, expectation x will become equal to integral x square by 2 dx plus integral x by 2 dx for 1 to 2 plus integral 2 to 3 x into 3 minus x by 2. In the remaining portion fx was 0, so there will be no term here. So this is equal to half 1 by 3 plus, here the integral will become x square by 4, so 1 by 4, 4 minus 1 plus 1 by 2, integral of 3x is 3x square by 2 minus x square will give you x cube by 3 for 2 to 3. So it is equal to 1 by 6 plus 3 by 4 plus half, the value at this is 27 by 2 minus 6 minus 9 plus 8 by 3, which can be actually simplified. There may be some other case also where it looks that the expectation will exist, as we have seen here in the second example. The integral itself is divergent, and therefore we are directly concluding that the expectation does not exist. However, there may be a case where it looks that the integral will exist, but actually it does not exist. Let us consider the density 1 by pi into 1 by 1 plus x square. So it is a valid probability density, as can be seen easily. The integral will be tan inverse x, that is equal to 1 by pi, pi by 2 plus pi by 2, that is equal to 1. So it is a valid probability density. However, if I look at expectation of x, a common mistake here is that here one can think that it is an odd function and it is over a symmetric region, so it should be 0. However, the property of the even function or odd function is applicable when the integral is convergent. Here if we look at integral 0 to infinity 1 by 1 plus x by 1 plus x square, then it is equal to log of 1 plus x square, which is actually divergent. Therefore, expectation x does not exist. If we look at the shape of this curve, actually at x equal to 0 it is 1 by pi, and if we look at the shape of this curve, then here it is at x equal to 10 it is 1, and thereafter it is reducing. From various curves here, for example, we found the expectation to be the middle value. Here the expectation does not exist, here it is somewhat different. So we are tempted to consider something like a concept of symmetry. We can define symmetric distribution as a random variable x is symmetric about a point alpha if probability of x greater than or equal to alpha plus x is equal to probability of x less than or equal to alpha minus x for all x. In other words, we can say f of alpha minus x is equal to 1 minus f of alpha plus x plus probability of x is equal to alpha plus x. If the random variable is continuous, this term will vanish and it will be simply a relationship between in the CDF at minus and plus point. Suppose I take alpha is equal to 0. In this definition, if we take alpha is equal to 0, then this condition is reduced into simply f of minus x is equal to 1 minus f of x plus probability x equal to x. If x is continuous, the condition is f of minus x is equal to 1 minus f of x, and if it is density, so you will have so if you see this distribution, it is symmetric about 0, here the distribution is symmetric about half, etc. You may also define a discrete symmetric distribution. Probability x equal to say minus 1 is 1 by 4, probability x equal to 0 is half, probability x equal to 1 is 1 by 4. So, this is symmetric about 0. We notice here some properties about the expectation function. For example, if I define y is equal to a x plus b, where a is any non-zero real number and b is any real number, then if we consider expectation of y, then it is expectation of a x plus b. It will become equal to expectation a times expectation of x plus b. In general, we can define expectation of a function of random variable also. For example, if I have expectation of gx, suppose x is a discrete random variable, then we can consider it as if x is discrete, we can define it as integral gx fx dx if x is continuous. The definition is subject to the condition that this summation or this integral must be absolutely convergent. So, absolute convergence is required in order that this expectation of gx is well defined. Another question arises at this point, that how do we define the expectation of a mixed random variable. So, for a mixed random variable, the expectation would be simply the value multiplied by the probability plus the integral of the density multiplied by the value. So, that means in the discrete and the continuous case, we separately evaluate it. Let us look at example of this mixed random variable. So, here expectation x will become equal to 0 into 1 by 4 plus x into 3 by 4 dx 0 to 1. So, this is equal to 3 by 8, which is actually less than half. This would have been the mean if the random variable was completely defined as 1 for 0 to 1, the probability density function. However, here the 1 by 4 probability is taken over by the point x equal to 0, therefore the average waiting time has reduced and it is now 3/8, it is not half. Next we discuss the concept of moments of distributions. So, let x be any random variable. We define mu k prime is equal to expectation of x to the power k. This is called kth moment about the origin, or kth non-central moment about kth non-central moment. Observe here that if I put say k is equal to 1, then mu 1 prime is nothing but expectation of x, that is the expected value. So, here we are getting the, if I am considering x equal to k equal to 2, k equal to 3, etc. So, basically we are able to define higher order non-central moments. So, if you look at expectation of x, in what way it is a moment? So, if I consider say a weightless bar with say weights attached, here at the point say x1 we attached weight px1, at x2 point we attach the weight px2, at the point say xn we attach the weight pxn. Suppose it is attached to two hinges with zero friction, and if we consider the balance point at the point of equilibrium or the center of gravity, that will be sigma xi pxi, that is the moment or the first moment of this. In a similar way, if we consider a metallic bar with the density say fx at the point x, suppose this is point A, this is point B, then if we consider A to be x fx dx, then this is denoting the balance point of this or the center of gravity of this bar. So, that is why this mu 1 prime is actually the first moment about the origin of the random variable. We also define mu k, that is equal to expectation of x minus mu 1 prime to the power k, or expectation of x minus mu to the power k. The first one we can usually denote by mu, the arithmetic mean. This is called kth central moment. In particular, mu 2 is called variance of the distribution. Let us look at the significance of this mu 1 prime and mu 2 in particular. So, mu 1 prime, as I mentioned, it is denoting the measure of central tendency or the center of gravity or the point of equilibrium of the distribution. We may also be interested in knowing how the values of the random variable are varying with respect to its mean. To get its measure, one may look at the values of xi minus mu. Now, if you take the average value of xi minus mu or x minus mu, then expectation of x minus mu is expectation x minus mu, which is actually 0. So, this does not give you any information. This is basically because of the fact that the plus deviations and the minus deviations from the mean, they cancel out each other. So, mu 1 is actually 0. However, to get a better measure of variability, one may look at the squared differences. So, we look at xi minus mu square and then we take the average. So, that is known as the variance of the distribution. We also define a quantity called standard deviation, that is equal to square root of variance of x. So, this gives a measure of the variability of the distribution of the random variable. It is obvious that if we are considering k to be positive integral values, then there will be a relation between mu k and mu k prime, which is expressed as the follows. So, if we consider say mu k is equal to expectation of x minus mu to the power k. So, using the binomial expansion, this becomes x to the power k minus k c 1 x to the power k minus 1 mu plus k c 2 x to the power k minus 2 mu square minus and so on plus minus 1 to the power. So, the first term is k c 1, so k c k, and you will have minus 1 to the power k mu to the power k. So, if you look at this, it becomes mu k prime minus k c 1 mu k minus 1 prime into mu plus k c 2 mu k minus 2 prime mu square in particular. We can write say mu 2 is equal to mu 2 prime minus 2 mu 1 prime mu plus mu square, which is equal to mu 2 prime minus mu 1 prime square, or expectation x square minus expectation x whole square. We may also observe one thing here, that since mu 2 is greater than or equal to 0, this implies that expectation of x square is always greater than or equal to expectation x whole square. We also have a relationship between non-central moments and central moments in the reverse direction. That means, we may interpret mu k prime as expectation of x minus mu plus mu to the power k. Here we consider this as one term and this as another term. So, this becomes expansion of plus k c 1 expectation of x minus mu to the power k minus 1 mu and so on, that is equal to mu k plus k c 1 mu k minus 1 mu plus mu to the power k. In particular, mu 2 prime is equal to mu 2 plus 2 mu square mu 1. So, 2 mu 1 and mu plus mu square. Now, this term is actually 0. So, this means that mu 2 is equal to mu 2 prime minus mu square. We also define absolute moment. So kth absolute moment of is defined as expectation of modulus x to the power k. We also consider, say, beta k is equal to expectation of modulus x minus mu to the power k. We also define what is known as some factorial moments, expectation of x into x minus 1 up to x minus k plus 1. This is called kth factorial moment of x. This is kth absolute moment about origin, and this is kth absolute central moment. In all the definitions of the moments, the basic thing is that these expectations must exist. For example, expectation of modulus x to the power k must exist. Expectation of modulus x minus mu to the power k must exist. That means the corresponding integrals or the summations must be absolutely convergent. In some cases, a lower order moment may exist, a higher order moment may not exist. Let us take one example. If I consider f x is equal to, say, 2 by x cube for x greater than or equal to 1 and 0 for x less than 1. If we consider expectation of x, then it is equal to integral 1 to infinity dx, that is equal to 2. If we consider expectation of x square, then that is equal to 2x square by x cube 1 to infinity dx. Clearly this is divergent. So a lower order moment may exist, but a higher order moment may not exist. In the next classes we will define some further characteristics of distributions. Basically these moments or other characteristics, actually like mean or variance, they explain the nature of the random variables values, how the random variable is taking values over the range of the values with what probabilities. So we will look into these things in the next lecture. Thank you.